Hey everyone, how's it going today? So, I'm gonna just quickly touch up and follow up on yesterday. Um, yeah, I think that Siddhartha Gautama had some ideas, man. So I'm gonna start with that. We did some math stuff too, but uh, just a little thing about the five precepts. So, cause like it was difficult because I Buddhism is like morphed a couple of times. There's like I think Chan Buddhism and a couple of others, um, which is more closer to a religion. Um, and I just wanted to like see what like the original, like the core teachings were, right? And it's there's the Four Noble Truths, right? Suffering, the origin of suffering, which is suffering arising from attachment, craving, and ignorance. Dukh, suffering dukh, that's dukh. I don't know how like the a is there, it's like dukha, but maybe it's because of Sanskrit. um I just know the Hindi version. I don't know how to say this. Some of the Nirodh, the cessation of suffering. Suffering can be overcome by eliminating attachment, craving, and ignorance. Mug, I guess, the path to the cessation of suffering, the Noble Eightfold Path is the way to end suffering, right? And accepting pain is part of it. Um, at least, right? Um, you have the Eightfold Path, understanding the Four Noble Truths, cultivating thoughts of kindness, compassion, and renunciation, speaking truthfully, kindly, and constructively, acting ethically and avoiding harm to oneself and others, earning a living in a way that does not harm others, make an effort to cultivate wholesome mental states and abandon unwholesome ones, paying attention to the present moment without judgment, developing mental focus and concentration through meditation, impermanence, all things are constantly changing and therefore nothing is permanent. Anat, at least I think that's how you'd say it, non-self. There is no permanent, unchanging self or soul, right? I don't know about the or soul part. I'd have to dig deeper into this specifically, but unchanging self. There is no self. That makes sense to me. Um, Everything arises in dependence on other factors. There is no ultimate independent origin. Um, which I think to me is like about circularity, about how everything's circle. I think time is also being seen in that way, maybe in cyclical ways. Karma, the actions have consequences shaping future experiences. Compassion and kindness, showing kindness and empathy towards all beings. And the five precepts of refraining from killing, stealing, sexual misconduct, lying, and intoxicants. I'm definitely not good with some of those. The killing thing, I mean, I love meat. I'm sorry. I can't. And the triple gem of Buddha, Dharma, and Sangha, taking refuge in the Buddha, the Dharma, and the Sangha, the community of practitioners, right? And Dharma is his teachings, but Dharma is also seen as like responsibility or duty. There's like a few different interpretations of Dharma. Wait, I had a page about that. Dharma as duty, as cosmic order, righteousness, individual purpose, guiding principle, right? So it's like, I feel like here, when people, because in a couple of different places when I was looking, and maybe this is my interpretation, to be honest, I'm doing an interpretation of kind of an interpretation because it's an AI summary, not me actually reading it, the real text, which I should maybe at some point in my life. Um, taking but like, I feel like dharma, or the concept of dharma, it's projected as like the eightfold path, like that is your dharma. But dharma, I think, comes from an older space, and one interpretation is the eightfold path. And like, but the thing is, within that there is nuance, right? Um, that kind of is explained by these other ways of seeing dharma, right? Dharma as individual purpose, right? This is an important one because it's like everyone's circumstances are different. So how you follow the eightfold path is different per person, right? In that way, and they have to find their sense of duty and where they fit in the order. Um, and these are the steps that you can take, right? Now, I don't know specific, I mean, I saw another like generated thing about accepting pain in Buddhism and how that's essential to um uh breaking the cycle of suffering. And this is not something I have on this series of tabs here, but I did look it up. And essentially it's like a cycle, right? There is the aversion to pain, right? Fair, easy to understand concept, right? No one likes pain, emotional pain or mental or physical, either way. And you run away to pleasure. And then because things are impermanent, for some reason, this thing will go away at some point, right? The most tragic thing uh, about love stories is that they don't end with a wedding, they end with a funeral, right? Everything ends, everything dissipates. But even in smaller ways, if you're into video games or whatever, like eventually the luster wears off, or like, the thing breaks or whatever it is, right? Which brings you back to pain, and then you run back to pleasure. So you have to just accept the pain and not like run away from it. You don't seek out pain, right? That's not what you want. Because if you're seeking out pain, in some ways it's a perverted type of pleasure. Like thrill seekers, or if you're a cold showers guy. I'm a cold showers guy, so I'm not knocking cold showers. But yeah, that's so if you accept that pain truly, then you can break this cycle that you're continuously going in on, right? That it is an emotion that is a part of you. It's not necessarily rejecting pleasure per se, I think, but it's about not running away from pain. At least that's the way I interpret it. Um, Anywho's, I feel like, I don't know, man, there's something to that, in my opinion. Suffering, see, samadhi, the origin of suffering. Suffering arises from attachment, craving, and ignorance. Suffering can be overcome by eliminating attachment, craving, and ignorance is the way to end suffering. So I feel like Nirod is where like you are accepting the pain. You have to accept it, right? And you can't there's many layers to it before you actually start accepting it, which is kind of what I went through yesterday. Um I feel a lot better today as well, actually. It's not bad. It's really not. I mean, I feel like certain points of the day today I'm like, that I was just like annoyed at or whatever, but it didn't affect my actions or even my capability to do what I wanted to do. Like, okay, this sucks. I'll do what I want in this way. Uh, Very specifically, I got dragged to uh, do some chores for the home that I didn't really want to go for, to be honest. I was just like, and I was like, okay, you know what? Let me just like read this paper I've been trying to read, like in the car right there, as much as I can. I'm stopping, I'm thinking. I even took like a voice note for an idea I had. I was like, okay, fine, rather than just sitting there and be like, I can't do anything other than like start my phone and like stay outside and be like, I'm not at my desk. I need my desk to work. Nah, you don't need your desk to work. You don't need anything to work, honestly. I mean, okay, that's not 100% true. You'll need a few tools of the trade of whatever trade you have. If you're a carpenter, you need, you know, your hammer, your wrench. If you're a software dev, you need a laptop. You need some basics to work, right? But if you want to do something, the bare minimum is much lower than what people are actually willing to accept. I used to have like these giant and this is something I espoused in the productivity space, like to myself and my friends, obviously not online. Like I had like these two really big ass monitors. It was LG Dulux, so they were like essentially two 16:9 monitors on top of each other, and that was not necessary at all. I like barely worked. And the funny thing is, when I stopped caring, like, oh, I need to like hook up my laptop to these things because I take my laptop out or whatever, right? Or if I left them both plugged in because I had a work laptop and a personal laptop, I'm like, oh my God, that's like so much effort every time. I just never used it, right? I'm like, even when I decided, like, okay, I'm just never going to use the work laptop on this, it's just going to be perma connected to my own machine. Still never used it. Um, it wasn't until I stopped bothering to think about it and just like opening my laptop and just work because it's like, oh, I'm don't have like the same environment between work and home, so it's hard for me to get used to it. Plus, it's like I was using a Mac at home versus a Linux at work. And just like excuse it. And once I got rid of everything, I'm like, okay, I'm just use the laptop. Fuck it. I don't need a mouse, no keyboard, no nothing. It's like, oh, okay. Now I'm working way more. So in the productivity space, yes, that's true. But like, I think outside of that, you don't you don't need many things to do anything almost. Um, right? And that was the example of that today. Like I could have just been like annoyed the entire time, or I and let that annoyance build into other emotions because emotions are there in your head. There's like a baseline just feeling of whatever that triggers negativity inside you, and then you start putting a layer on top of that and top of that, like, well, this sucks because this person is like that, and also like traffic sucks and whatever, and then it's like anger or it's some other form of negativity that lashes out, and then when you if you're lashing out at anyone, like even in a mild way, like I don't mean like yelling or anything like that necessarily, you end up feeling bad because like, why did I do that, man? That was mean, unnecessary, right? And then either you just like kind of let go of it internally or whatever. Um, like you can just be like, okay, I'm annoyed, so it's feeling, it's another feeling, but for that to work, like even joy or like things like that. It's not that you can't feel joy. My dad was listening to like, I think one of those YouTube clips of like some stand-up special, and I was laughing my ass off, like, because I was hearing it in the background while I was working. I was hearing him watching it, I mean, and it was funny as hell. So it's you don't have to cut off joy per se, but you just don't need to be bothered about chasing it. I think that's really the key here, right? And maybe I'm taking a more uh, liberal approach to the interpretation. Maybe what he actually meant was what he actually said, but I don't know. This is how I think. So this guy's got something going. Back to figuring out lesson 11 and eigenvalues and eigenvectors. Oh yeah, hit that flip switch. You guys weren't seeing that coming. So actually, I went through the previous one and for some reason, like it just flowed. Like today, it made a lot more sense to me. I didn't go through the example here, I could have, I guess. Maybe we can. Let me go through what I did so far, and then we can come back and maybe figure out the example. But oh, this is the definition, and I was like, what is this stuff going on? It's about the characteristic polynomials, diving deep into that. But the main question here was understanding exactly what eigenvalues and eigenvectors were. And like initially, I got sidebarred by the polynomial stuff, right? And I still did. I was like, what are the roots of a polynomial, right? Because that's kind of, I remember being my major malfunction. Also, I was exhausted. So they're the values of the variable, right? Essentially, right? Or the potential values of the variable. So, right, for x squared plus 2x plus 1, I think that's x plus 1 squared, right? Which is, which means that x is equal to -1, right? And you could have other factorizations like x plus 3 times x minus 4, uh, where x would be therefore equal to -4 or positive 3. In both of those cases, those are second degree polynomials, aka n is 2, right? So if that made complete sense to me, like that shouldn't have taken me effort to figure out. And honestly, I could have figured out from just picking apart the expression, but I just I don't know why I forgot the terms, I guess maybe, or maybe I just never learned them. I don't know. Sometimes people learn things in different contexts because I wasn't like raised in the US or anything like that, despite my very obvious American expression. This was me confirming what x squared minus 2x plus 1 was. There's also x plus 1 and x minus 1. What's that? I think that would be this one, right? I think, yeah. Oh, 2x. Oh, they just plugged it into I forget what this thing is called. Um I know it's derived from Pythagoras in some way. Something like that. Anyways, it's what is this called? I remember the thing. Like it's negative, okay, even without looking at it, let me see. Negative b plus or minus root of b squared minus 4ac over 2b. Right? Yep. Oh, it's b squared minus 4ac. Oh, it's 4ac. Okay, I screwed that up. Yeah, whatever. Doesn't matter. Um, okay, so this is the defining property of orthogonal matrices. Then its transpose is indeed the same as its inverse. So I ended up Googling this, going back to ChatGPT, coming here. So scrolling back to the top, right? Wait, no, this part is finish because I want to understand how you actually calculate the eigenvalues and vectors. This already was like, what is going on? So I asked a follow-up question where it went deep into what that whole like equation was, right? So A is a original is like your it's a matrix. It's a real valued matrix. And it's a symmetric matrix. Symmetric matrix meaning that A equals A transpose, right? Symmetric matrix. Let's just Google that. Identical to its transpose. Yep. Okay. So symmetric matrix, it's the linear transformation you're starting with, right? Oh yeah, I think I didn't properly explain this to you guys. So this was fairly straightforward, right? Um, Essentially eigenvalues and eigenvectors, because I just kind of jumped off like talking about like the polynomial, then I came up here and then I said some stuff and then I moved on to the next one without really explaining this because I remember when we last spoke, I was like basically here. So essentially, if you have a matrix A that defines a linear transformation, I'm just going to tilt this a little bit forward. Um, and that's a real matrix of sum n by n, so it has to be a square matrix as well, which I guess if you're defining a linear transformation, that makes sense. Um, an eigenvector of that matrix would be one that if you apply the transformation that the matrix defines to that vector, the result will be the exact same vector scaled, and the scalar quantity is the eigenvalue. So that's the vector is the eigenvector, and the value that it's scaled by is the eigenvalue, right? It's pretty straightforward. Um, and since that can be represented as AV equals lambda V, that leads to the characteristic equation, which I'm assuming has other properties. But like, I didn't like dive deep into that because I'm like, I was reading this and I could just trust, I just kind of it made sense to me, kind of. I don't know how to explain it. I didn't dive deep into like why the characteristic polynomial is useful and stuff, because I feel like that's something we're gonna revisit again anyways. And I just moved on because it made sense to me, right? I looked up what the roots were. It makes sense that if you expand the determinant formula, it'll expand into a polynomial, especially as you get arbitrarily large, and it makes sense that this would be the roots would be the eigenvalues because a minus lambda I, right? So you're doing element wise reduction of that and doing the determinant, right? And lambda I is essentially the matrix where all the diagonals are the lambda values. You're essentially scaling each column by the eigenvalue, right? You're scaling it or subtracting it? Yeah, subtracting it. And then you take the determinant of that. That becomes a hairy equation that opens up to the polynomial. Okay, that makes sense. Sorry, I feel like I just started saying some circular stuff to try and explain this, which is exactly what I did. Um, we should just dive deeper into the characteristic polynomial at some point, maybe even in this video. Let's see how long I can go because I am tired. Um, this is the story of my life, right? I should try and do these earlier so that I can get more done, but such is life. Um, and the geometric intuition actually makes a lot of sense. So lambda will stretch if it's greater than one. If it's less than one, it'll shrink. And if it's negative, it will flip direction, right? Because that's true of any vector. That makes sense, right? If you multiply any vector by a value larger than one, it'll increase size. Otherwise, it'll shrink in size. And if it's negative, it'll flip and shrink, or, it's pretty straightforward. I did not go through this example over here. Um, because I moved right back to the original one here, and I started having problems because I was confused by this big equation with the Q's and the A's, not with the library here, this one, right? And I kind of started diving into that and what that meant because I wanted to know what that meant. So A is your original real symmetric matrix. Q is an orthogonal matrix, meaning that all the columns are orthonormal. Uh, well, I guess this is lambda. I don't know what this is. Like, I think that's capitalized lambda as well. So this is lambda. So that's lambda. That makes sense to me. What is the symbol for lambda? Let's just confirm that. I'm curious. Yeah, it is uppercase lambda, right? Is the diagonal matrix of eigenvalues, which is what this was here as well, right? Essentially, lambda I is just uppercase lambda, right? Because in this case, lambda is the vector of eigenvalues. Where's this? Oh, wait, sorry, lambda is not, it's literally just the eigenvalue here. Right, never mind. So that's not, those are not the same things. Where the eigens are all the eigenvalues. My bad. That's not the same. So, this is why we're on the road, why we are not there. What does A equals Q lambda QT literally encode? So this is where I got to, right? I understood that Q times lambda is just the scaled, is just each vector scaled by its accompanying eigenvalue, each eigenvector being scaled by its accompanying eigenvalue. Oh, wait, no, sorry. Yeah, okay, Q is all the eigenvectors, correct. Yes. And Q transpose is um actually the inverse also, because Q transpose is equal to Q inverse if Q is orthogonal, and that's what I was looking up over here. Wait, this was the roots of the equation. The Yeah, there you go. This is the defining property of orthogonal matrices. And I think I asked some. Oh, generally means okay. Why does orthogonal? I don't know why I googled that, or maybe I was trying. Outer products versus inner products. Yeah, I was a little bit confused by because I thought I mean I saw the term a couple of times while we were doing some of our previous videos, but I wasn't sure what it was. So I think there's inner products and there's outer products. So yeah. Um. Oop. But I get it now. It's essentially here, I'll just you know what? I'm gonna go back and show you here because I opened the same tab over here. It's essentially like the dot product is the inner product, right? So that's just x transpose times x basically versus x times x transpose, because the way you do matrix multiplication, like inner products and outer products, it's like I think the thing that I was thinking initially still applies, where and I had that confusion between dot products and matrix multiplication like way back at the beginning of this. It's weird, but I was kind of onto something, because when you do an inner product, it's technically the transpose of the vector times the other vector, right? Whatever that first vector is, it's the transpose of that. So it's, and then you do row column, right? So there's only one row and one column, so you get only one thing. But if you do um the outer product, you're doing the vector times the transpose of the vector. So each row, each column, column, row, column, if you want to see it that way. And that yields a matrix, right? So a dot product yields a value, and an out a dot product or inner product yields the value, and the outer product yields the matrix, right? Um, which also leads to an interesting thing where the inner product is only defined for equivalently lengthed vectors, but the outer product is not. Um, yeah, yeah, see, I just like started looking that up. This I think we Googled together in Lambda. So, yeah. The reason I was looking up outer products is because this next line is Q lambda times Q transpose. So Q is the matrix of eigenvectors, and the transpose is just making it so that each row is the eigenvector instead of each column, essentially. So each vector in the matrix holds um the first component, I guess, of each eigenvector. Yeah, right? Because that, right? And then this one will become this one. This one, no, wait. The rows and columns are swapped, right? So this, no, this becomes this, right? Then the second column becomes the second row, right? Yeah, that makes sense, right? Second row becomes, sorry, second column becomes second row, right? Uh, and therefore the first element in each will be in the first columns in the new matrix, which is the transpose, and then the first elements, sorry, the second elements of each eigenvector will become the second column. So each vector will be composed of that component of of the eigenvector in the transpose, which is also the inverse, because Q is also orthogonal, right? Because um eigenvectors are orthogonal, I guess. I don't know. Um, and then so when you multiply Q lambda by Q transpose, right? Um, you get the sum of the outer products, I guess. Um, you know what? I'm gonna do this by hand on video. I'm gonna plug in. Sorry, it looks weird for you guys because you guys see the presenter overlay. I'm just plugging in my iPad so I can screen share that. Uh, and to use my point, let's turn that off. Notes. Okay. Let me open up QuickTime Player. Option Command N. Oh, it's already connected to my iPad. That's nice. Just maximize the screen. All right, so make sure this is working. Yes, it is. Okay. So Q equals, or let's go with Q lambda equals lambda 1 v1 comma lambda 2 v2 dot lambda n vn. Okay, that makes sense. So I'm just gonna actually move this thingy. Is this fully charged? No, this is just at 59%. Drink some water first. Ah, let me put this into landscapes. It's better viewing for you guys. Okay. Make sure my the battery is starting to drain a bit fast. Let me put my laptop on charge as well really quickly. Not to be a shill, but power banks, a good power bank is awesome for this kind of stuff. you go. It's my laptop charging. And we're charging. Okay. Okay, so Q lambda is this, so let's expand on that. So Q lambda is essentially a matrix that then looks like this, right? So it'll be lambda 1 v 1, let's say 1. Just don't get the superscripts confused. I'm using the superscripts as just another index for like so v1 superscript 1 is actually um whatchamacallit. It's v1 superscript 1 is the first element of vector 1, right? So then that's lambda 1 v1 2 dot 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 lambda 1 v1 n, right? I'm gonna do that again. Lambda 2 v2 1 lambda 2 v2 2 dot 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 lambda 1 v2 n, right? Dot 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 dot. So that's lambda n v n 1 lambda n v n 2. Oops, sorry, that's n, not 2. And lambda n v n n, right? That makes sense, right? And then Q transpose, right, is essentially the transpose of weave of a Q, right? Transpose of Q. Actually, I think it's like this, right? So it'd be v1 1, right? And then v2, so from vector 2 element 1 dot 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 vn1 v1 2, so second element in vector in v1 v uh, what's the thing I'm looking for? 2 2, yeah, sorry. Brain farted. vn2 dot 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 dot. Dots are fun. Dots are fun. V2, oh, sorry, not V2. VN1, VN2, and then dot 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 dot. Oop. VNN, right? And so if we multiply these vectors, so we're taking this row, multiplying it with this column, right? So the result would be excuse me. Mm, V ugh, V lambda 1 V1 1, right, times V1 1 times V1 1. That'll be the first element. No, well, not the first element. Plus lambda 2v2 1 times v2 1 dot 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 lambda n v n 1 times v n 1. Is that correct? Lambda v n 1 times v n 1. Hope you guys can see the little highlighter. Yeah, you can. Right, and then there's this weird, I don't know what I did there. Ooh, that is not what I intended. I'm just gonna reverse that. Is there any way to dismiss this error? Nope. Okay, whatever. So let me just see if I can turn off the math results off. Did not help. Okay, that's fun. Okay. So you do row and column. So this, let's just call this E1, 1, right? So in this future matrix, E11 is this, right? And then what is E12, right? So the second element here would be let's see, E12 would be the same row, second column. So it's lambda 1 v1 times v12 plus lambda 2 v21 times v22 lambda n v n 1 times vn2, right? Right? Lambda 1 v1, lambda 1 v1, 2 v2, lambda 2 v2, then vn, lambda n vn, vn squared, not squared, vn2. Man, the double numbers is weird. So it's E12. Lambda n would be same thing. E1n. E1n equals, well, still the same first row, so I'm just gonna leave a blank space to fill that in a moment. Lambda 2 v21 dot blank space dot 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 lambda n vn1 times v1 1, add a 1 there, and that would be with vn1, no, yeah, the last column, right? So vn, is this correct? No, I messed up the transpose, so this is actually Vn, and this would be 1, 2, right? Super messy to read. Just gonna clean this up. Whatever. So that's V1n, V2n. There you go. That's correct, right? Yeah, because the rows become the columns. Okay, so I was screwing that up a little bit. Oh, for E11 and E12, I think that's fine. The second element in each vector, right? Then E1n equals lambda 1 V1 times V1n, V2n, and then VNN. V1n, V2n. I should have just like double subscript instead of double superscript. It's way more confusing this way, actually. But I'm gonna stick with it. Lambda n Vn dot Vn n. Okay, what is E12 exactly? Lambda 1 V12 plus lambda 1 lambda 2 V22 lambda n Vn2, right? V12 V22 Vn2 times so it's this second row, first column, V11, V11, V21, Vn1. Yeah? Yeah, okay. Okay, so how does this go back to the outer products? So the outer products, the sum of the outer products. So let's just say V1, right? So V, I'm just gonna do this. I'm just gonna double subscript it. Fuck it. V dot 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 V1n, right? Oh, you guys can't see that. Sorry. So let's say that's V1 transpose equals V11, V12, dot dot dot, V1n. Okay. Right. So it's lambda times this times this. So what does this result in? So we lambda times, well, this is going to lead to a matrix, right? So V11, V11, so V11, V11, then it'll be V11, V12. Oh, yeah, because we're just looking at V1 transpose basically. dot 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 v11 v1n, right? And then we do that process again. So with the second row, so v12, v11, v12, v12, dot 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 v12, v1n, and then v1n, v11, v1n, v12, v1n, v1n. Yep. This matrix times lambda. And then the sum of that. Why? Okay, v11, v11. I see that here. Oh, wait, no, sorry. Not there. I meant here. And then where the fuck is v21? It was all v11, right? Oh, you guys are seeing this and not this. I'm like looking at this and not even showing you what's going on. So I see v11 over here. Where's v11 and v12? Oh, it's over here. Oh, right, and that's in this position, 1-2 position, 1-1 position. This is the 1-1 position and the 1-2 position, right? And we get that as part of this and this, right? And we do that same thing for each vector, right? And that's what each element is the sum of those vectors. Oh, okay, so it does make sense. Math. Isn't that great? Okay, so I'm just gonna try and write this out formally because I'm understanding it, but I don't think if you get that you guys are necessarily able to see it. So I'm gonna try and write it out formally, and that'll help me also understand it a little bit better. Right, so for E1n, right, equals the sum of I equals 1 through n. So that's lambda I vi1 times lambda I vi 1 vi n, right? Oh boy. Formalizing this is difficult. Like I'm seeing it. Like I get it. But how do you formalize that? Okay, instead of trying to do it this way, let's try and do it with matrix notation, right? Because I did this out in vectors for me to be able to see it, but to formalize it, I think if I'm not using proper matrix notations and such, it won't make sense. So Q lambda equals the vector, essentially, of lambda v1 through lambda vn, lambda 1 v1, right? So all eigenvalues and eigenvectors, right? Yep. Then Q lambda, oh, not A, Q lambda Q transpose equals the sum I equals 1 through n, sum of outer products, right? Which is lambda I vi dot vi transpose, right? Yeah. Okay, so that's the sum of outer products. Now it's this, I mean, that I know from ChatGPT because now the formalization of the because is the hard part. Q transpose is essentially V1. It's the vector of the first elements. I'm just going to denote that like this. It must be a better way to form. Okay, I don't know how to formalize it. Fuck it. I get it. And I'm pretty sure this video is like crazy long already, so I think I'm gonna call it there. I get it. I think this makes sense to me. Um, since it makes sense to me, let's see what else we can do. Key viewpoint. Each term, lambda I, vi, vit, is a linear operator that projects a vector onto direction vi via vi transpose x. Okay, via the inner product, basically, of the eigenvector and x, and then scales by lambda. Then reorients along vi. I don't understand this part that well because I project a vector onto direction v, then scales by lambda, and then reorients along v because v are mutually orthonormal. These projection and actions don't interfere. They add up independently to give a. Okay, this is something that needs understanding. That's for another day. See you guys. Have a good one. Stay curious. Accept your pain. Live life. Bond to others. See how you are a tiny piece in the order of the universe. Have a great one.